experimental and computational simulation of wind pressures and forces on buildings. Dr. Karim, thank you, and we see your screen.
Great.
So, if you want to start, thank you.
That saves me the question. Thank you very much. The purpose of my presentation is to give you some introduction to experimental and computational simulations of wind pressures and forces on buildings to get everybody up to date, because all of you probably don't have the same level of understanding of wind, which is quite complicated, but many of you have good experience with earthquake engineering, and I'll try to use examples and try to show the differences between the two during my presentation. Just to begin with, we got different types of winds. If you have heard, you saw that people are talking about hurricanes, downbursts. We have tornadoes, downburst, big cells. So the wind conditions in all these storms are not the same, but the building codes treat them the same. That is one of the issue, which is one of the current topic of interest to many people. Just to see what happens in a hurricane or a tornado, you can see some of the tall buildings and some of the low-rise buildings, how badly they perform once the wind is very extreme. We almost had a tornado many years ago enter city of Miami, but it didn't, luckily. But hurricanes have ruined many tall building facades. From the left is Hurricane Alicia in Houston, in Hong Kong, and in Dallas on the right-hand side. It's not only the glass which is damaged, it also sucks up the stone cladding, like the stone or the facade, as you can see in the middle of this stucco type can also be peeled off. And this is during Hurricane Andrew in Miami area, where the whole building site was pulled out. And now China is facing the same issues. These are some of the very tall buildings in the coastal cities of China. And during Typhoon Mangkhut, these are the pictures taken out of that storm. More recently, there was a typhoon which sucked up some people out of a building. So this is becoming a life safety issue at the same time, what happens to the cladding of the building. At the same time, I think others will talk about, it's not only the tall buildings and others, the communities can be wiped away in tornadoes because of this event. So back to our structural dynamics expertise, we go back and look at what are the loads caused by wind. And as you can see from this particular sketch, we got spectrum, which shows you the bandwidth of energy over frequencies in earthquakes, wind, and waves. As you can see, more flexible structures would be more sensitive to wind, and more stiffer structures would be more sensitive to earthquake. The difference is that how do we transform these earthquake ground motion to the structure, and how the wind fluctuation is transformed to a load. That is a little bit more complicated because there is no one-to-one transformation, and that's where things become more complicated. Just I made this list. You can read it in more detail at your leisure when you have time. But what I'm saying is the wind loads depend on shape and profile of the structure, where an earthquake mostly depend on mass distribution. Two buildings with the same mass distribution but totally different shape can have very similar response, but not in case of wind. We lack a transfer function from wind fluctuations to the load, but in the case of earthquakes, it's the mass times acceleration, relative acceleration. Both are direction dependent. Response normally in wind is linear, and in case of earthquakes, as you know, is mostly non-linear. Time history analysis requires an ensemble of surface pressure time histories, which cannot be directly obtained from wind velocity fluctuations. You have to do some theory, which is currently intractable, or you have to go to wind tunnel or to some CFD application. Response in wind is normally limited to lower modes, and in case of earthquakes, higher modes are normally included. Now I use this terminology of near source and far field ground motions and bring that to wind. The near source events are more like a downburst and a tornado, and far field is like the atmospheric boundary layer, which runs over a long stretch of land and arrives your building. And that's where all our building codes are dependent on. This is a little scary diagram, but this is what it is. This is the energy in the wind that is in front of the building. After, you see these big globs of eddies, they wrap around the building, they stretch, they tilt, and that's where things become more complicated. And we cannot find pressure on the building surfaces by relating them to wind velocity fluctuations. So that's where I think I will talk in the later, we do experiments or CFD, or machine learning might be helping us in this particular direction. Just to give you a little bit more, here is a tall building and a low-rise building, and you can see as wind approaches, we have the wind cannot follow the profile of the building, and it separates and creates these vortices, which are bad for pressure fluctuations. Like we see on this building, the wind is coming from this side to that. You can see these pressure fluctuations. And if you look at the time histories, they look very non-Gaussian. And the same thing is for low-rise buildings as well. We have pressure acting, wind coming on the building, but the load effects like the moments here or the shear or anywhere in the building, we can see they also still have some non-Gaussian features. So if we treat them as Gaussian, we may be under-designing our structures. So what do? Here is a just general diagram. We want to tailor our structures, be those high-rise or low-rise. We have various options. We can learn from full-scale monitoring, which you will also hear later in this workshop. Codes and standards are always there. And we have wind tunnels and we have computational techniques. In order to manage all this, we have a cyber infrastructure platform, which is design safe, which provides you the platform as well as the data depositing capabilities. And the SimCenter is the one which will help provide tools into these computational methods so that you can address some of the problems. Just to begin with a wind velocity profile, if you have wind blowing over a smooth land as compared to a built up, you can see the difference in the shape of the profile. And that is what is defined in the building codes. Either if you go using fluid mechanics background, it is what we call as a logarithmic law, which is normally good for the lower part of the profile. So the designers like to use a power law, which is more convenient because you don't have a log in there. So this is the most popularly used profile description, where alpha, if it is very small, it represents a more open country conditions. And if alpha becomes like 0.35 or 4, it becomes more like an urban condition. Now, this is for atmospheric boundary layer situation. What happens if we got a downburst or we got a tornado or we got a hurricane? That is going to change in that particular case. Just to, without defining those, just to give you some experience, what happens when we change those. See, in early days, when the wind engineering started in England, they used to use aeronautical wind tunnels, and the profile was what we call uniform profile. And here's the response of a building, which happens to be the World Trade Center Tower, because it was tested there. And they found that the response was like 50 feet. That's too much response for a building to be experiencing and be a real building. Then they realized, oh, now we need to add some turbulence. You see, everything got suppressed a little bit. Then they said, no, the profile has to be matched. The response even changed further. And this would be a profile of a typical downburst, where the response would be also different. So inflow conditions are going to be very important for how our structures behave, because this variation in mean wind velocity changes the aerodynamics. And I can get into the details, but we have different cells of vortices which are not coherent with each other. That's why we get a response which is a little bit more subdued as compared to in these types of flows. In case of a hurricane, there are a lot of models being developed where we can define this velocity profile, which we need to use both for our experimental simulation or CFD type. Just very quickly, I won't go into the details because in my diagram, I had a wind codes and standards. So basically wind loads and standards, all wherever you go, they're all based on Gust loading factor approach back to 1967 by Professor Davenport. And it basically deals with buffeting action. That means only in the direction of wind. That can be mathematically tractable, but once you go to a crosswind or torsional response, there are issues. We cannot use that theory. So that's why many building codes have some empirical descriptions, and ASCE has it in its commentary using a database approach. So what is in that? Basically, the building codes ASCE standard 7 is when you start with a wind velocity fluctuation, you convert into wind force and you find the response. This is in time domain, and this goes down in the frequency domain, where for a long wind or buffeting response, all these intermediate transfer functions are known, so we can take care of that. Let me take you to 1963, that wind tunnel of World Trade Center Tower. When they found that the response was like 40 to 50 feet, they came to my professor advisor, Professor Jack Cermak, who was an expert in boundary layer wind tunnels. And here they are in that wind tunnel with that model without Les Robertson, Helen Davenport, and Jack Cermak there. And these two models were tested there, as you can see, city of New York at that time. And this is the model. Both are looking from a different angle. Sorry about that one. So that's where the beginning of wind load testing, especially on taller building, started. And now here is a collage of various wind tunnels. Like this one is at RWDI. And as you can see, you just saw this one. Wow. This is at University of Florida. And this is our modest wind tunnel at Notre Dame. This is at Colorado State, where the Sears Tower was tested. And this is one of the largest wind tunnels at one time, but not anymore. It is in Scuba, which was built for a Kaishi-Kaiko bridge, where you could put 2 tennis courts inside that building, that wind tunnel. Then we have certain wind tunnels where we look at the cross-sectional property of the bridges, or for others, long towers, and then use mathematics to expand that for the overall modal analysis. Now, there's another types of wind tunnels coming up with a lot of multiple fans. It started in Japan, and now it is going everywhere. I think there are 7, 8 of those available at this time. And here is a numerical wind tunnel also, which we developed because certain things we wanted to do, like flipping a plate in the wind tunnel to create a downburst. So we couldn't do fast enough. So then we went to CFD to try to recreate that situation. This is just a little collage. I forgot to mention one of the wind tunnel, probably the largest wind tunnel in a university setting in Southwest Jiaotong University in Chengdu. And here's a Milano wind tunnel. That's also a very sophisticated wind tunnel in Polytechnic Milano. And here are some of the tests, just to give you a flavor about bridges. This happens in full scale, and this is what is happening in the wind tunnel. Most of these are bridges, and this is a building studied. Scales. Scales is the most important thing. I think a lot of questions have been coming up, and I think you can have a full 1-hour lecture on scales. But just to give you an example, we have to worry about scales. If you don't honor them, then the results would not mean anything. And I think this thing which Rindam mentioned, about more than a decade ago, our group and Polytechnic Milano tried to dissect the power spectral density of wind into 2 parts, the lower frequency and the high frequency. And we did that theoretically in order to model the effects of turbulence on bridges, because it was not done before in computationally. But I think the work done at WOW has perfected it for modeling that in wind tunnels so that they can use large scale models to test, because they only take care of modeling the high frequency part of the turbulence, and the low frequency part they manage using theory. To find forces and structure, there are 3 types of models. One thing is that you just put pressures taps on the model and see how the wind can create pressure fluctuations, and you monitor that. But the trouble is, if you have, like when I was doing my PhD, the largest number my advisor had was 6, because pressure transducers then used to be about $5,000, and now it is about 10 cents. So you can see the difference. So I had 6 pressure transducer and tried to develop overall spectral distribution of loads on the building. But now these days, we can put 500 to 600 pressure taps, so they can give us all the information as you can see on the left-hand side. The best thing is to have the pressures because you don't have to worry about the mode shape and others. But there is another workhorse of wind tunnels. It's called force balance. That is primarily a replica model, but underneath it is connected to a balance. So what it does is that integrated effect of all the loads is monitored by that balance. And it so happens, I won't go into the details of the study here, but this is the building model on that one. What happens is if you develop an equation for the modal force of a building, which is sort of given by this very simple expression, and if you develop base bending moment caused by some arbitrary wind loads, they both happen to be only scaled by a factor of height of the building. So what they started doing was to measure the base moment divided by h, you got the generalized loading in any direction in the first mode. And remember that first mode has to be linear, not any arbitrary shape. Of course, there are ways to correct some of the things, and then one can get into this very standard random vibration approach in order to find out the mean square value of the response. Digital wind approach is a cyber-based data-enabled design. This connects to the multiple pressure point fluctuations which we have. So what it does is it provides you a hybrid combination of wind tunnel and with CFD with structural models, as earlier Dr. McKenna mentioned. This creates real-time digital simulation of building response. And it has the ability to include nonlinearity because we have time domain. We can add damping devices, as was mentioned earlier. And we are able to explore different structural system with fixed profile or multiple profiles. There are two papers. One deals with high-rise buildings using this one, and other one deals with the low-rise buildings. Just to give you a very quick overview of what happens. Here we got a building in which we have a lot of pressure fluctuations. We could go to a database like ours or TPU, Tokyo Polytechnic University, or we could have a CFD information. You fill in all the structural details, they go into the data, and then we can get the results of various kinds in which we are interested. This particular version was based on getting output as the equivalent static load because most designers like to use that. But now with SimCenter, we have developed that you could get time histories of response at various levels. Same thing is exactly happens in the low-rise building, where the data comes either from wind tunnel or in the future, I would see there will be depots of CFD pressure fluctuations and rest remains same, and we can get the response of any desired quantity which we are interested. This is very powerful. It gives you a time history of the resultant load effect, and you can pick up the extremes the way you want. In older days, we have to play with the game of switching pressures at different places, use influence lines to come up with something. We used to get the same things, but I think now we can do many things much faster and in much more expedient way. What do we do in the end? Just pay attention, please, on the right-hand side. We have to couple that with the local climatology. As you can see, the Boston, New York, Toronto, and Montreal, most of, except New York, everybody has southwest as a dominant wind direction. Same as in Chicago. New York is dominant by this southeastern because of the hurricanes. Then what you can see, the directionality of the wind. If you have a building like Burj Khalifa, its shape changes at every height, as you can see barely in this yellow diagram, and the vortices being shed. So the designer has the option in this particular case to rotate the building in such a way that it does not go into the worst the wind direction, which could give you the maximum type of load effects. Just one slide that there's a lot of buildings monitored. The Chicago project many years ago, that was Dr. Tracy Kajewski's doctoral dissertation. And then we went to Burj Khalifa, and then we had access to the data in one of the world's most instrumented building, a tower, which was utilized in analysis of results. But in this particular workshop, you won't get much more into this, but this is becoming very critical. And now, especially the monitoring the facade, the cladding is becoming very important. And we have very special type of crawling robots and drones going around trying to find out what really happened in this case. Now, very quickly, computational fluid dynamics. I cannot give you a complete lecture, but I just want to familiarize you with the three letters RANS, LES, and DNS. The DNS is a fully resolved Navier-Stokes equation solution, which normally only few researchers can do. RANS is the one which is the workhorse of CFD, in which what we do is here's the wind fluctuation spectra. In RANS, we do not resolve anything numerically, but in fact, we use a modeling of the turbulence, which helps us to do it very fast. In large eddy simulation, that is in between the two. What we do is we take our spectra, we cut it into two parts, just like I told you about the partial simulation, but this is the reverse now. In partial simulation of the wind tunnel, we don't worry about this part, we take care of it theoretically, but we model this part, the higher frequency one. But in LES, the reverse happens. We resolve the low frequency part, and the high frequency part, we use a model. But the difference is the cutoff. In case of wind tunnel, the cutoff is somewhere here, but in LES, we want to stretch it as far to the right as possible, because that way we can numerically resolve some of the eddies and everything. But always remember this thing, that CFD is something nobody believes except the person who made it. An experiment is something everybody believes except the person who made it. But I don't think that is all the way true, but there are some questions one can raise with experiments. So always CFD doesn't have to go to experiments to compare the results. I think it should work both way around, and it is happening that way now. Now here is the equivalent of your wind tunnel, numerical wind tunnel. There is in the middle, you got your simulation domain. We can use any type of the model you have. You have to worry about resolving these fine scale structures. We have to worry about higher numbers, grid resolution, and the wall boundary conditions. And we have to worry about the inflow, because that is just as critical as it is in the wind tunnel. So this gives you an overall picture what one would do, or some of you are already doing it. Here comes a synthetic turbulent inflow. There are various ways to create turbulent inflow. Some of them results in duplicating what we do in the wind tunnel. Let the flow self-develop over certain roughness, but that's more expensive and time consuming. So we take advantage of synthetic turbulence by combining stochastic simulations with some fluid mechanics to make sure that our flows are divergence free. There's a list of models, and we have developed a inflow modeling in the SimCenter, which is TINF, T-I-N-F, and here are some examples of those. We have 4 different methods which are available, and then I'll show you in a minute. Well, one can also look into GPUs, because these type of simulation inflow conditions can be done, and we have successfully used GPUs also to simulate inflow condition. Here are some examples, very quick. TINF was a tool, which I said, and here are some examples of visualization of vortexing. One would go and resolve it even more. We had to do this quick for demonstration purposes. Here is an example of a city with left side diagram shows steady inflow, and the right hand side shows you the turbulent inflow, and the mixing what happens in between, and the scale structure of flow in between buildings would be different from in both these cases. Here's an example where we go to a bigger city. Here's a little try we are doing with the city of San Francisco, where these buildings are dynamically modeled, and they are scaled up 100 times in case of a wind coming from one direction. This is in collaboration with Tsinghua University. And I think down the road, we will see that, in old days in fluid mechanics, we used to do smoke visualization or dye in a water tunnel. I think very soon we'll have all these things digitally done. And here is one example. We did the model part of city of Houston after a windstorm while investigating the glass damage. And here are some of the flow patterns which help us to understand what was happening in this street canyon, which was corroborated with the flow visualizations. And later we did pressure measurements on the building to see what really was happening in that particular case. Those of you who are involved in aeroelasticity, now the trouble becomes more complicated. We got three equations to worry about. We got equations of governing fluid, governing grid is moving, and so is the building moving. So here is example of a two-dimensional structure which is vibrating, and one has to, the numerical methods become more sophisticated because a three-field FSI problem, and it defines a nonlinear index to differential algebraic system of equations, which the stability becomes a little bit of an issue, and one has to make sure that they are satisfied. Coming back to researchers who are more excited to do new things, you know, the one on the top was 1963. Professor Alan Davenport set up the framework for what we call wind loading chain. But this is only good for stationary winds and linear forces and everything. We have extended that in the bottom, which I go through, which I call it a generalized wind loading chain, which this represents a time frequency rather than just the frequency. So it's a time frequency. It is an evolutionary Gust spectrum. So it tells you with time how the energy in the wind changes. So one has to determine a corresponding force kilogram, which also is time and frequency dependent. And of course, we have our transfer function, which also changes. For example, if it's a degrading system, its frequency with time would change, and so would the damping value. So once you combine these all together, this becomes the evolutionary response spectrum. Those of you who are interested in non-stationary effect of wind on structure, here is your tool to work on establishing and elaborating what is given in here. This could be done either those of you who are familiar with the evolutionary power spectral density from earthquake engineering, or it could be also used in wavelet domain. Those of you have preference of using wave. Both are basically equivalent to each other, and in a paper in Journal of Structural Engineering, this has been shown, the results from these together. So for researchers, I think modeling of wind spectra, because we have a number of expressions for the wind spectrum, Davenport spectrum, Harris-Kaimal spectrum, but we need to develop a more unified expression which is representative of typical wind conditions in non-stationary wind. It will be different for downburst, would be different for tornadoes, different for hurricanes. So I think that's where I suggest that we should look more into design evolutionary Gust spectrum, which just like design spectra for earthquakes, we should look into a similar approach, because otherwise every storm is different. We cannot compete, take care of everyone, but if we standardize it, that this is what we are going to design for, I think we will have expressions available for all these as well. Now, what is the future of computational wind engineering? I believe that this is going to be a fusion of CFD, because CFD has a lot of roadblocks. And to get results for to resolve finer scales, we need a lot of resources which are becoming available. But still, to run a large eddy simulation for a little building, you'll need about 3-4 weeks on Stampede currently, and that is too long to wait. So there are other techniques that are becoming in CFD which are relying on data analytics or machine learning, and some part of that is stochastic emulation of what happens. And one of them is a multi-fidelity modeling. For example, one of my students is working on, she's simulating things using RANs, which is very fast and quick. And some or other develop a bridge between large eddy simulation and the RANs, which is more quickly obtained. So this type of a bridge is more some sort of a surrogate modeling or machine learning, which help us to develop that. And she has shown a lot of success. Again, one bridge is not going to be good enough for all types of buildings and structures. Of course, we have to classify certain regions and certain types of structures which would do good. So I think this particular diagram is the future of computational methods in wind engineering. And just to give you an example here, using Bayesian deep learning, here's a building, tall building, The wind is approaching into the screen. These are the pressure fluctuations. These are the ground truth. This is our prediction using a very small data. And here is, even we can tell the error how much is and what are the uncertainties. Same thing here, field regressor is a very powerful approach. And I just want to give you the example when I told in the beginning of the lecture that we don't have a mathematically tractable relationship between inflow fluctuations in the wind and the pressure fluctuations because complex turbulence is too complex. Here as we have a case, we have some field which is connected to, through some transformation, some output fields. One input maybe could be multiple outputs. Here is an example. Here is a ground truth. And this is what we predicted using a field regressor, which is again has Bayesian deep learning and other machine learning tools. Also gives us the error, which is in our representation of that. This particular example happens to be a plate bending under lateral pressure. So I think this is where we will be going to take care of those challenges which are currently holding us from doing most of the things, because we have to have a multi-pronged approach in computational techniques in order to overcome some of the handicaps we have. And this is the last slide to connect. All what we are doing is, this is our same standard peer-based, performance-based design equation in which we will be looking for, tools we are developing would help us to get aerodynamic analysis and structural analysis to eventually give us fragilities of various kinds. Interstory drift fragility is very relatively easy, but once we come to the cladding being pulled away or rupturing, and same thing with low-rise buildings. And I think that is going to be the topic which Tracy will be pursuing. And I think we have already gone a little bit quick overview by Professor McKenna and the types of samples we are doing. We have we can have a stochastic simulation. We can have wind tunnel database assisted using low-rise, using high-rise, CFD for beginners and CFD for experts. And we can also run it through Tagora to get reliability analysis or do sensitivity analysis of our variables which we have. Of course, stochastic simulation plays another role. We can stochastically simulate a lot of loads, and here is a summary of those. Most popular method is spectral representation method. But once we come to thunderstorm, downburst, we have to use more wavelet-based or evolutionary spectra-based methods. And there are a lot of papers coming out on enhanced methods. They add computational efficiency. What we have done is we have started capturing that in this particular smelt. And this one is a stochastic, modular, and extensible library. So far, we have only populated with one type of simulation, which is based on that method, which I just met. In future, we will be expanding this for people to be able to use these, not only for their research, but also for the classroom teaching. And it is currently already being used at several locations. I think my time is running out. I can just skip these. We have a non-expert and we have expert. It's using OpenFOAM. We have the option to use various turbulence models. Turbulence inflow comes from TIMF model. We have automatic mesh generation. And I think that's where I should end because I'm just running into the next presentation. Thank you very much. I will be very happy to interact one-to-one with anybody who wants to understand. I think before we jump into wind tunnel or computational methods, it's good that we understand the basic concepts, the various differences between different types of wind conditions and how they affect our results so that you can design and tailor your experiments and your simulations accordingly. Thank you very much.
Thank you, Hassan. This is Tracy. I was just wondering if you would have a quick opportunity to respond to one of the questions that came in during your presentation from Maria. She was asking, can you explain the difference between the coastal or offshore wind profile and that which you would encounter as it moves inland?
If I could go back to my original. Here is the coastal on the left side, and here is the urban environment. Once the roughness on the ground means buildings, they will obstruct the flow. So this particular profile becomes steeper as it approaches on land and up to in an urban area.
So Maria, I don't know if you jump into the chat if there was more clarification you were seeking regarding that, but Hassan was just referencing the change in the profile. There's change in the turbulence properties as well, and the height at which gradient wind speeds are achieved. And Maria has followed up, is this the case even if you were talking about large offshore structures? Would there be any change in this, Hassan, based on the kind of structure this fluid is interacting with?
Well, large offshore structures will be somewhere even on the left of this. There the profile would be a little bit more fatter than this one. Like typically 0.1 would be the exponent alpha for that one. By the time you reach the coast or the very near the coast, it might be 0.12, 0.13. So the profile in the for offshore structures is totally a different area because you have interaction with wave also. So that's a little bit more complex. But if you just want to use basic design procedures, the profile would be even, I would say, more.
So I think in short, Maria, as you work with the team to support your proposal development or your project idea, the more we can understand the positioning of these offshore turbines, I think, or whatever structures you're dealing with, then they can understand a little bit better of the profile needed and can tailor the experiment or even the computational simulation accordingly. Hassan, there was a second question just pointed out. It says the points you raised on the side of CFD are interesting. Do you see a value in improving the FSI simulations as well to account for structural and elastic deformations such as damage and improve modeling of the structure to fluid interface?
Yes, because if you are just looking at very tall buildings, like the one you are seeing in New York City now, or for bridges, this is cables. This is highly desirable to have this capability. But I think this area of a little cladding piece getting pulled out, then it will sort of flutter around the building. That is a local fluid structure interaction problem, which is essential also because that is the one which would enhance the stresses in the components and eventually the peel off.
So hopefully that response satisfies that question. Thank you, Hassan. Perfect. Yeah, so it appears that we've resolved those two questions in the chat and we are perfectly aligned with our timing to move into a break.